right, so we're going to continue on with infinite series, and for the next few sections, that's our focus. In an infinite series, our goal is to determine whether it converges or diverges. In the event that it does converge, it would be nice if we could figure out what it converges to, which is what the series is equal to. Unfortunately, we can't always determine that. In this section, 10.3, we're going to look at two specific infinite series, the geometric series and a telescoping series. These two series, we can determine convergence, and we can also determine what it converges to. So first of all, we're going to look at a geometric sum with only n terms. So it's a finite sum. And we're going to look at the sequence a times r, a times r squared, and so on. And here r is going to be our ratio. So we can define a partial sum, so that would be our s sub n, adding up the first n terms. So it would be a plus a times r plus a times r squared, and so on. The nth term is a times r to the n minus 1. So let's first pause and see why the exponent on r is n minus 1. So notice that our first term is actually a times r to the 0. Next term is a times r to the 1. This first term a, that's actually a sub 1. Our a sub 2 is a times r to the 1. A sub 3 is a times r squared. So you notice our indice starting with 1. Compare that to the exponent on r. The exponent on the r is always 1 less than our index, which is why we end up with r to the n minus 1. So this finite sum can be written using the summation notation. The expression is a times r to some exponent k, and since the first exponent we start with is 0, my k value will start with 0, and then I end with exponent n minus 1. So that's just a partial sum of n terms. So let's see if we can create our infinite series. So let's say we're going to start with k is equal to 0. We have the same expression, but now we're going to go to infinity. If I want to determine whether this converges, and if it does converge, what it converges to, what I do is I take the limit of the partial sum, and that was from our previous section. But we already defined what that partial sum was, so we're taking the limit of this summation. Something that I would like to bring your attention to is our starting k value. All three of these following series are equal, but look at their starting k values. They're different. And look at the expressions. They're a little bit different. So it may come up that some theorems or some process will be easier to apply if we change our starting k value. So this is the series we're looking at. We started at k is equal to 0, and our expression is a times r to the k. So let's say that I want to start with k is equal to 1. From my original series, all I did was I added 1 to my k value. Well, if I add 1 to my k value, it might be easier if we see it here. If I add 1 to the k value, to even things out, I have to minus 1 from the k value in the expression. So I start with k is equal to 1, but notice I made up for that by subtracting 1 from my k value. Well, let's say that I start off with k is equal to -1 instead of 0. Well, in this case, I'm subtracting 1 from my initial k value. So to make up for that, I need to add 1 to my expression, which means it's going to be a times r to the k plus 1. So you can always change your index, or what you start with. Whatever you add or subtract to your initial k value, you're going to add or subtract from the expression. So this also works if it's a finite sum. So let's just say that instead of ending with infinity, let's just say that I ended with 2. So I'm going from k is equal to 0 to k is equal to 2. Well, if you're changing your starting and your ending, you actually do the same thing. So if I'm going to add 1 and start with k is equal to 1, then I'm going to add 1 and end at 3. If I subtract 1 and start with k is equal to 1, I'm going to subtract 1 and end with 1, because that's telling me how many terms. If I start with k is equal to 0, I go 0, 1, 2. I have 3 terms. If I start with k is equal to 1, I have 1, 2, 3. 3 terms. If I start with k is equal to negative 1, I have negative 1, 0, 1. Gives me 3 terms. Let's go ahead and verify in example 1 if we can actually change our starting by changing our expression, and we'll just go ahead and expand these out. Let's look at the first one, k equal to 0 to infinity of 0.2 times 0.5 to the k. So if k is equal to 0, 0.5 to the 0 is just 1. Our first term is 0.2. Plus, if k is equal to 1, then this is 0.2 times 0.5. If k is equal to 2, it's 0.2 times 0.5 squared, and so on. I think 3 terms is enough. Now let's compare this to the next summation. So I'm just trying to show that these are all equal to each other. We start with k is equal to 1, so we started at 1. We added 1 to our starting value. We subtract 1 from our expression. And this is to the k minus 1. Is it the same? Well, when k is equal to 1, then this is 0.5 to the 0 power, which is 1, and we get the same first term. If k is equal to 2, sorry, I'm going to infinity. If k is equal to 2, this is 0.5 to the 1 power. So it's still 0.2 times 0.5. And then when k is equal to 3, this is 0.2 times 0.5 squared. And they'll all be the same. Well, let's say we start at k is equal to negative 1, and we're going to infinity. So since we're subtracting 1 from the starting, we add 1 to the expression to make up for it. And when k is negative 1, this is k plus 1 is to the 0 power. So we get 0.2. K is equal to 0. It's 0.5 to the 1 power. And then when k is equal to 1, this is 0.5 squared. So all 3 of these series are the same. So let's say we do have a geometric series. Well, remember, this is not a sequence, this is a series. But we do have some similar properties with reference to r, the ratio r. If the absolute value of r is less than 1, then the value of this infinite series is simply a over 1 minus r. So it converges. And in fact, it converges to a over 1 minus r. Now this a is really important. That's going to be the first term. So you need to know what that is. And r is important, your ratio. You need to know what your ratio is. What's not important is your starting k value, because we saw previously that it really doesn't matter what k value you start with. So this is not important. Now, in the event that the absolute value of r is greater than or equal to 1, then our series is going to diverge. Let's look at example 2a and evaluate the series, or state that the series diverges. Well, one thing I could do is I can write the expression so it looks like a times r to the k. That way I can identify my a and I can identify my r. So 2 times e to the negative k, that's the same as 2 times 1 over e to the k, or 1 over e in parentheses to the k power. So 2 would be my a, and 1 over e, that would be my r. And then that's to the k power. Well, sometimes we kind of don't want to do that. Sometimes it's just easier to expand your series out. The first term is your a, and then look at what you multiply each term by to figure out what your r is. I think I'm going to rewrite this series, because I don't like the negative exponent, as 2 over e to the k. So if I were to expand this out, when k is equal to 0, this is 2 to the e to the 0, plus when k is equal to 1, this is 2 over e to the 1, plus 2e squared, and so on. So notice that the first term is always your a value. So in this case, my a is going to be 2 over 1, which is simply 2. Now I'm multiplying each term by 1 over e, so I could see that r is equal to 1 over e. So again, you can just take your expression and try to write it in the form a times r to the k, or you can simply expand out your series and look at the first term as being your a, and then try to figure out what you multiply each term by to identify your r value. So this is the geometric series. I noticed that the absolute value of r, 1 over e, is less than 1. So I know it's going to converge. And in fact, it's going to converge to, so this series is going to be equal to a, which is 2, over 1 minus r, which is 1 over e. Now typically we don't leave our answer as a complex fraction, so if I simply multiply top and bottom by e, I get 2 times e over e minus 1. I personally don't care which one you write as your final answer, but again, my lab might get a little bit picky if you leave an improper fraction. Why don't we look at another example? In this next series, it's kind of hard for me to see if it's a geometric series. So I could try to write this in the proper form, a times r to the k. What I do notice is that the denominator is going to be 2 to the k times 2. So if I take out the 1/2, and the 1 over 2 to the k would be 1/2 to the k power, then I have my a, my r to the k. And I can see my a is 1/2, and my r is also 1/2. But I didn't have to do that. What I could do is simply expand this out, as when k is 1, this is going to be 1 over 2 squared, plus k is 2, 1 over 2 to the third, plus 1 over 2 to the fourth, and so on. So when I expand it out, I can see, yes, this is a geometric series. This first term is my a value, which is 1/4. And then I could see my r is equal to 1/2. That's what I multiply each term by to get to the next one. And I know that the absolute value of r is less than 1, so this is going to converge. It's actually going to converge to my a value of 1/4 over 1 minus my r value of 1/2. And if I simplify that, I'll get 1/4 over 1/2. This will actually simplify to, I believe, just 1/2. Okay, one last example. Notice I'm not really doing the diverging one. That's easy. If the absolute value of r is greater than or equal to 1, then it just diverges. You don't actually have to figure out what it's equal to. Okay, so it looks like this is something to the k power. It looks geometric. If I expand it out, when k is equal to 0, natural log of 0.6 to the 0 power is simply 1. Plus, when k is equal to 1, this becomes natural log of 0.6 plus natural log of 0.6, but this whole quantity is squared, and so on. So a is equal to 1. R is equal to natural log of 0.6. That's what we're multiplying each term by to get to the next one. Well, in your calculator, if you put in natural log of 0.6, you'll find that it's negative 0.5. So the absolute value is actually less than 1. I know it converges. What does it converge to? It converges to 1 over 1 minus the natural log of 0.6. So this would be the exact answer. If you want to plug this in a calculator, you can get approximately, we'll go 1 decimal place, approximately 0.7. So one thing that we can use these geometric series for is we can use it to write a repeating decimal as a fraction. So if I wanted to convert 2.31, and the 31 is going to repeat, to a fraction, I could first write it as a geometric series. Now I'm only really concerned with the portion that repeats. Notice that the 2 does not repeat. So the first thing I'm going to do is I'm going to break this up as 2 plus 0.31. And I really don't care about that 2, I'll add it in later. The 0.31 repeating, this is what I want to write as a geometric series. So remember, this is equal to 0.31, 31, 31, 31, and so on. It's an infinite series, but I want to break it up into a sum. So the strategy is to just break it up to its repeating parts. This is going to be equal to the first term in my series will be the 0.31. And then if I look at the next term, I'm going to put in 2 zeros and then a 3-1 plus, look at the next term, it's going to be 2 4 zeros, 1, 2, 3, 4, and a 3-1. So I can write this as a infinite sum. The 0.31 would be my A. So what is my R? So this would be my AR, AR squared, and so on. So to get from 0.31 to 0.0031, I'm multiplying by 0.01. So R is 0.01. So I know this converges, since that is less than 1. This is going to converge to A over 1 minus R. All right, so that's going to be equal to 0.31 over 0.99. And if I simply move the decimal over 2 places, top and bottom, I get 31 over 99. Now remember, that was just the repeating portion. This whole expression, this whole repeating decimal, is actually 2 plus 31 over 99, which we can simply do without a calculator. It's going to end up being 229 over 99. And we've used our geometric series to convert from a repeating decimal to a fraction. So in the beginning I said we were going to look at 2 infinite series where we can actually determine what they converge to in the event they converge. The second one would be this telescoping series. So it's called a telescoping series because if you've seen a telescope, they expand out. In a telescoping series, it's typically easier if you begin with k is equal to 1. Because the process for a telescoping series is to be able to figure out what the partial sum S sub n is. So we need to figure out the first n terms. That's easier to do if you start with k is equal to 1. Example 3 says determine if the series converges or diverges by first finding a formula for the nth term of the partial sum, then evaluating the limit as n goes to infinity of S sub n. Notice in example A, this is not a geometric series. I'm subtracting 2 terms. So if you see 2 terms that look similar and they're separated by subtraction, that's a hint that it may be a telescoping series. So the first thing we need to do is we need to figure out what our S sub n is. S sub n, since I'm starting with k is equal to 1, I'm going to end at n. And I need to expand this out. The reason why I need to expand this out is because I need to figure out specifically an expression for S sub n. So remember in the very first section, 10.1, these partial sums, we actually computed our S sub n. Well, we still have to do that. Okay? Our S sub n is not simply 1 over 2 to the k minus 1 over the 2k plus 1. So I'm going to expand this out. When k is equal to 1, this is 1/2 minus 1 over 2 squared. So I'm just going to write that, well, maybe I won't multiply it out. Maybe I'll just keep it as 2 squared because I'm lazy. Plus, the next term is going to be when k is equal to 2, so it's going to be 1 over 2 squared minus 1 over 2 to the third, plus when k is equal to 3, I have 1 over 2 to the third minus 1 over 2 to the fourth. And then we're going to go to the nth term, and that's why I wanted to start with k is equal to 1, because to get to the nth term, all I have to do is just substitute n for k. So the nth term would be 1 over 2 to the n minus 1 over 2 to the n plus 1. So these are the n terms that I'm adding up for my partial sum. Now I have to find an expression for my S sub n. So what I'm going to do is, and this is why this is a special series, because of the subtraction in there. So notice, because of the subtraction, some of these terms will cancel when I expand or telescope this series out. So I have to look at the pattern of canceling. So if you notice here, I have a minus 1 over 2 squared, but then I have a plus 1 over 2 squared. So if I were to get rid of these parentheses, the minus 1/4 and the plus 1/4 will cancel. So the pattern of canceling is, I'm going to look at the last and the first term, and they'll cancel. For example, if we look at the second set of parentheses, the minus 1 over 2 to the third and then the plus 1 over 2 to the third will cancel. So in the second set of parentheses, I'm canceling the last term with the first term of the next set of parentheses. So my pattern of cancellation is last, first, last, first. So I go last, first. Not everything will cancel. What's left over is going to be your S sub n. So what's left over is 1/2 minus 1 over 2 to the n plus 1. Now it's important, and what's important here is that you have n terms because we're computing S sub n. And this is one of those cases where if you're not starting with k is equal to 1, you might want to change your indice. So remember, this is my S sub n. To figure out if this series converges, all I have to do is take the limit as n goes to infinity of my S sub n, which is 1/2 minus 1 over 2 to the n plus 1. And when we take this limit, the 1 over 2 to the n plus 1 is going to go to 0. This limit is equal to 1/2. So what that means is our series converges to 1/2. Or in other words, the series our initial series, 1 over 2k minus 1 over 2k plus 1, that's equal to 1/2. So not only could we figure out that it converges, we also know what it converges to. Let's try some more examples with a telescoping series. So in part B, I notice that this is not a geometric series because there's 2 terms, but they are separated by subtraction. So since they are separated by subtraction, I'm thinking probably telescoping. I'm starting with k is equal to 2. So to figure out the first n terms, maybe I want to switch this so that I start with k is equal to 1. So you can do that. If I subtract 1 from my starting k value, I'm going to add 1 to the k value underneath the radical. In other words, this is the sum k is equal to 1 to infinity of the square root of k plus 3 minus the square root of k plus 2. My S sub n, I'm just going to go ahead and expand this out to the n terms. So when k is equal to 1, this is the square root of 4 minus the square root of 3. Okay. Plus, when k is equal to 2, we have the square root of 5 minus the square root of 4, plus k is equal to 3 square root of 6 minus the square root of 5, plus, and so on. So my nth term would be just substituting in n for k to get the square root of n plus 3 minus the square root of n plus 2. Now let's find the formula for s sub n by noticing the pattern of cancellation. So it looks like I'm going to cancel the square root of 4's. So that would be first, last. And then I cancel the square root of 5's, which would be the first term and then the last term. Cancel first term, last term. What's left over is my s sub n. In this case, it's going to be the negative square root of 3 and plus the square root of n plus 3. When I take the limit as n goes to infinity of negative square root of 3 plus the square root of n plus 3, it's going to be equal to negative 3 plus infinity, which is simply infinity. So this series diverges. And let's do one more example. This is a fun example because this is not a geometric series. Notice that in the denominator I have k plus 2 and k plus 3. So this is not a geometric series. It's not a telescoping series because I don't see a subtraction. The key to telescoping is you want to subtract two terms. However, this could be written as a subtraction if I use my partial fractions from chapter 8 to write this as a over k plus 2 plus b over k plus 3. When I do the algebra, what I'm going to get is a equal to 1 and b equal to negative 1, which gives me this subtraction. I get the infinite series from 0 to infinity of 1 over k plus 2 minus, because b is a negative 1 over k plus 3. So now notice that this is telescoping. I'm starting with k is equal to 0. So if I want my first n terms, I could change it to k is equal to 1, and I could subtract 1 from my k values. Or you don't really have to do that. If you notice that when you expand it out, you're going to stop at 1 less. However, I am going to rewrite this as k equal to 1 to infinity of 1 over. So I'm adding 1 to my start. I'm going to subtract 1. This becomes k plus 1 minus 1 over k plus 2. So my s sub n. My s sub n is going to be equal to 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1, 2, 3 would be 1/4 minus 1/5 plus my nth term is going to be 1 over n plus 1 minus 1 over n plus 2. So is there a pattern of cancellation? It looks like the last term and the first term cancels. Last, first, last, first. What's left over is going to be 1/2 minus 1 over n plus 2. So when I take the limit as n goes to infinity of 1/2 minus 1 over n plus 2, notice that the 1 over n plus 2, 1 over infinity, that goes to 0. So this is simply 1/2. So my series converges to 1/2. So let's put this all together. Let's go ahead and evaluate the series or state that the series diverges. Well, when I look at part A, I notice that it's probably a geometric series. But notice this is 2 times k for the exponent. So just using properties of exponents, this is -1/3 squared, which would make it a 1/9 to the k. Okay, so that's easy for me to see that my r is 1/9. I could expand this out. When k is equal to 1, I'm at 1/9, plus when k is 2, I'm at 1 over 9 squared. K is equal to 3, 1 over 9 to the third. Notice that I'm not starting with k is equal to 0. I'm starting with k is equal to 1, but the starting k value in a geometric series does not matter. First term is always your a. So that would be 1/9. And then notice that to get from one term to the next, I'm multiplying by 1/9. So in this particular case, my a is 1/9, my r is 1/9, which is less than 1, so it does converge. Since it converges, it's going to converge to a over 1 minus r. So definitely need to simplify that. 1/9 over 8/9 would be 1 over 8. If I look at part B, I don't see geometric here. What I see is possibly telescoping. I'm going to try to write k times k minus 1 in the form of a subtraction. So I have a over k plus b over k minus 1. And then solving, I'm going to get a equal to -1, b equal to 1. All right, so this is going to be equal to the sum, k equal to 3 to infinity, of -1 over k plus 1 over k minus 1. I do get a subtraction. Let me go ahead and rearrange this. So I get 1 over k minus 1 minus 1 over k. And then notice I'm also starting with k is equal to 3. Maybe I want to start with k is equal to 1. Well, I wonder if I'm going to run out of space. So I'm subtracting 2 from my starting. This becomes k plus 2, subtract 2, add 2. K plus 2 plus 1. And 1 over k plus 2. My S sub n is going to be 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5 plus the nth term is going to be 1 over n plus 1 minus 1 over n plus 2. Pattern of cancellation would be the last term with the first term. Last, first, last, first. My S sub n is going to be 1/2 minus 1 over n plus 2. So when we take the limit, as n goes to infinity of 1/2 minus 1 over n plus 2, that's equal to 1/2, and our series will converge to 1/2. Okay, so that's it for this section.